morning and welcome back. Today we'll consider parallel transport, and to an extent this is the showdown of the whole business about connections, because using parallel transport, especially on a vector bundle, we can define, for instance, a covariant derivative, and that's of course very useful. But as I cautioned you at the beginning, the notions of connection and parallel transport and covariant derivative, they're all to be distinguished in general. So what's parallel transport? Well, the basic idea is the following. And let me illustrate it in a picture. And this picture deals with a principal bundle P down to a base manifold M, and this be a G principal bundle, a principal G bundle. And for the purpose of this illustration, let's say the dimension of the Lie group is just 1, and the dimension of the base manifold is 2, because then I can draw a nice picture. Now, so assume somehow this is our base manifold, and at each point there is attached a fiber which is isomorphic to the group. All right, so everywhere there are these fibers. And now what we're considering is a curve in the base manifold. So this is the starting point. So say there is a point A in the base manifold and a point B in the base manifold, and we consider a curve through the base manifold. Let's call this curve gamma. Okay? So now, given this curve, we would like to lift it to the principal G bundle, and there would be various ways to do that. But a particularly interesting case is the one where the principal G bundle is equipped with a connection 1 form. So let's also assume that we have a connection 1 form, omega, which of course induces or defines at each point of each fiber a little horizontal space. So if this is the point P in the fiber, on the fiber bundle, then this green guy is the horizontal space at this point. But of course, at other points in this fiber, there are other horizontal spaces. So this is what a connection 1 form induces in each fiber, and so this continues. So at this point, it may look like this. Then at this point, look like that, and here may look like this, and so on. And this is, of course, throughout the principal bundle. So this comes from this connection 1 form omega. And now we have a special way to lift this curve gamma from the base manifold up to the principal bundle, namely simply by virtue of going to a particular point P here and asking, is there a tangent vector, is there a curve up here? So let me draw it. It may look like this, okay, such that I use the bundle projection pi here to map the curve down. So pi projects down along this fiber, that the projection of the blue curve is the curve we started with. That's the first condition. Second condition, that this blue curve goes through a specific point here, because I could also look at the point that goes through here and has this property. And further, that the tangent vector to this lifted curve has 0 vertical component, and that it lies entirely within this horizontal subspace, okay, in such a way that the push forward of this tangent vector here in this horizontal subspace under the pi map is the tangent vector down here. Okay, so these are 4 conditions that must be met, and then we have a unique lift of this curve down here to the blue curve up there. And in that case, and I will write this down formally, but that's the idea, in that case, this blue curve will be called the horizontal lift of gamma, and we denote this by a little arrow here. The idea will be that, of course, I can do this now for every point in a fiber, and this way, given a curve, I'll get an isomorphism between all the fibers where the curve, along whose base points the curve passes. Okay? But this isomorphism, so how this point is being mapped to this point is being mapped to this point, crucially depends on how the curve connects the 2 fibers. If the curve connects the same 2 fibers in another fashion, there may be a different map of this point to, say, this point. Okay? So this mapping between the fibers will depend on what path in the base manifold I choose. And that this is dependent on the path in the base manifold will lead to a notion of holonomy, which we're going to talk about. Okay? So that's the basic idea. And once we have that, we have such an isomorphism between various fibers along a certain curve. If the fiber, we can also push this. This is a principal bundle picture, a very special principal bundle picture in order to be able to draw it. But we will push the whole formalism to the associated bundle. And once we did this, we can look at very specific associated bundles, namely associated bundles that are vector bundles. And there we can then use this isomorphism between fibers to push forward or pull back along this isomorphism elements in this fiber in this way to define a covariant derivative. So this is the path starting with a connection on a principal bundle, how we will come to a covariant derivative on some vector bundle on which the group G acts from the left. Okay, so this is the outlook, this is the intuition. So now let's try to write this down more precisely. So first we start with the idea of the horizontal lift of a curve. So definition. We first start with let gamma be a curve, and we're actually only interested in the curve in this case a closed domain 0, 1, because we're always now going to look at starting at one fiber and going to another fiber. Okay, so let gamma be such a curve in the base manifold. Okay, so it's important that this is the base manifold. And with gamma of 0 being a point A and gamma of 1 being some point B in the base manifold. Okay? Now, then the unique curve called gamma up arrow, which is now a curve from AB into the principal bundle. Of course, this curve lives up here. Then a unique curve through a point gamma arrow of 0, and this point we'll call P, and this must be a point in the fiber over the starting point A. So this must be in the fiber over A, okay, for which which satisfies well, first of all, we need that the curve gamma up arrow, the horizontal lift it's going to be called, projects down to the curve we started from. First condition. The second condition is that if we look at the vertical part of the tangent vector to the lifted curve, so what's the tangent vector to the lifted curve? We denoted this by x and then the name of the curve here at each point along the curve. So gamma hat of lambda, if lambda is the curve parameter. The vertical part vanishes everywhere. So for all lambda in AB, okay, there's no vertical part. And the third condition is that if you take this tangent vector and you push it forward along the projection map, so pi push forward of x gamma up arrow gamma hat of lambda, so everywhere along the curve, what you obtain is the tangent vector to the original curve in the base manifold x gamma gamma of lambda everywhere along the parameter range. So this curves which satisfies this is called the horizontal lift. The horizontal lift of gamma through P. And indeed, this uniqueness here solely stems from this condition that you pick a particular point P from where you start, and then it's fixed. Yes?
Then you get a problem with the parameter range? Inserting lambda in the curve gamma.
Oh, I'm sorry. This is, of course, the parameter range is 0, 1, and the endpoints are A, B. I'm sorry. So we parameterize from 0 to 1 and starting from the points A and B. Okay? Thank you. So, of course, if we start at another point P here, or P prime here, then we get another curve that connects all these fibers, and which is a horizontal lift of gamma, but it's a different one because this is the one, maybe one should indicate this, this is the one through the point P, whereas this is the horizontal lift, gamma horizontal, through the point P prime at the starting point here. Okay? So there are various horizontal lifts of one curve, but once you fix one of the points it goes through, it's a unique curve. One can prove this, but it's actually quite obvious. So, okay. So now this is a definition that allows you to check once you have a horizontal lift of a curve that it is a horizontal lift. Now we need a strategy to actually calculate to write down an explicit expression for such a horizontal lift of a curve. So our strategy to write down an explicit expression for a the horizontal lift. So if I talk about the horizontal lift, I always chose a point P it's supposed to pass through, is to proceed in two steps. So the first step, which we'll discuss in turn, the two steps. The first step is to generate the horizontal lift from some arbitrary curve in the principal bundle that projects down to the original curve. So generate the horizontal lift by starting from some arbitrary curve delta, which is supposed to be a curve also from 0 to 1 in the principal bundle that projects down to the original curve. So if you execute the projection map after this curve delta, you get that curve. By action of a suitable, and of course this needs to be said immediately what I mean by suitable, of a suitable curve G, and this is now again a curve from 0, 1, but with values in the Lie group of our principal bundle. Namely such that the horizontal lift at a certain parameter value lambda be given by the arbitrary curve delta there, but then moved within the fiber at each point by the value of the curve in the group G of t. Okay? So the idea is, if I draw this picture again, so this is again our principal bundle. So assuming that I have my curve gamma in the base space, so this is the curve gamma I wish to lift. Okay, so curve gamma. And now the idea is take any curve, green curve delta, in the principal bundle as long as it projects down to the curve gamma, which is of course ensured if it runs through the same fibers. Okay, so this is the arbitrary curve delta. Well, not so arbitrary, it projects down to gamma, and whatever the parallel transport, the horizontal lift of the curve gamma is, so this is the gamma up arrow, I would like to generate it by starting from this delta curve and finding at every point the suitable g, the suitable little g, that takes me from here up there. Okay, and that's of course then a curve g, because this g will change from point to point. Okay? And it's absolutely clear that I can do this. No matter how exotic this delta here is, depending, of course, what it is, I will be able to find a group element that takes me to another point in the fiber, namely precisely the point where I want to go. But of course, I need to say this imposes a condition on this g. Right? So that's the strategy by which we proceed here. Okay. By a suitable curve. And in fact, we will write down an ODE, an ordinary differential equation for this curve in the group manifold. And if that ordinary differential equation is satisfied, it will be guaranteed that acting with this curve in the group on the arbitrary delta curve in the principal bundle will get the horizontal lift of gamma. And of course, this ODE for this curve must involve the delta, because it will be a different curve in the group depending for different deltas, right? So that's the strategy we're going to follow. Okay. Questions so far? Yeah?
Why do we use the open in
It's to be seen topologically. So, thank you. Okay, so that's the first step. And then once we have this differential equation, well, let me write it down. The suitable curve G from 0, 1 to G will be the solution to an ordinary differential equation with the initial condition that the curve at 0 in the group is an element G0, where G0 is the unique group element for which the delta at point 0, the value of the arbitrary curve in the principal bundle at 0, is taken to the point P in the principal bundle through which the lifted curve is supposed to pass. So if this is the point P, right? Okay. So there will be an ordinary differential equation, and the second step in the explicit construction of the horizontal lift will then be an explicit solution of the ODE. So we will explicitly solve the ODE for the curve G by a path-ordered integral we will locally explicitly solve the ODE by a path-ordered integral over the local Young-Mills field. Which you remember is a Lie algebra valued one form on the base manifold that contains all the information about the connection one form if one throws in as well the knowledge about the Maurer-Cartan form of the Lie group, which we did last time. Okay, so what we did last time with the Young-Mills field, we'll now use explicitly in order to obtain an explicit expression for the horizontal lift. Okay, so, well, let's start. So at 1, we have the theorem. The ordinary differential equation for the curve G is add G inverse push forward of the one form omega in the principal bundle evaluated at the point delta of lambda. So we move along this arbitrary curve and we plug in a tangent vector in the principal bundle, which will just be the tangent vector to this arbitrary curve along at each point delta of lambda, okay, plus the Maurer-Cartan form along G of lambda. So here it's also G of lambda inverse. So it's G of lambda inverse. And it's the Maurer-Cartan form here. And this is along the tangent vector. Now this is a different construction along the curve G, so that's a tangent vector in the group. It's therefore a tangent vector in the group. It's in the tangent space TG of the group G equals 0. Well, so this is the ODE to be solved with the initial condition that G of 0 be precisely that G0 we identified here. Okay. And indeed, this is a first order ODE. Which may not, in this abstract formulation, may not be obvious at first sight, but there is the tangent vector to the curve. So this is the G dot, okay? And so this is a first order ODE which we need to solve. Now, however, this is a theorem and it needs to be proven, but this is actually not too difficult. And of course, the proof amounts to showing that now taking the delta of lambda and acting on it from the right by G of lambda satisfies all properties of the unique horizontal lift curve gamma hat of a curve gamma where the lifted curve is through the point P in M. And that's the point appearing here. Okay? And so this goes to the new problem sheet, which I'll send to you today. Okay? So this is the task at hand, and you see the arbitrary curve from which we generate by this curve G in the group manifold, which we generate this lift, of course makes its appearance in this differential equation. It must. Okay. So from this we have an immediate corollary, and there it pays off what we calculated last time. And this corollary is that if G is a matrix group, so some subgroup of some GL, okay, if G is a matrix group, then the ODE takes the form so we remember that the push forward here simply amounted to taking the matrix and multiplying it from the left to the one-form field. So it's omega delta of lambda along x delta delta of lambda. So that, of course, remains. Okay. And then coming again from the right. So these here, they're now matrix multiplications. Okay. And but nevertheless, this is Lie algebra valued, this is group valued, but because we have a matrix group, the group elements can act by matrix multiplication on the Lie algebra elements. This is just, if you wish, a numerical coincidence here. But that makes it very simple. And here the Maurer-Cartan form we also calculated for this case, and we found that it's the inverse of the group element acting here, and it acts on, on the G dot of lambda, where the G dot is just the derivative of the matrix element. So there's another matrix multiplication here, the derivative of the matrix elements with respect to this lambda. So we wrote dg by dt or something, and that's this thing equals 0. And in this form, we of course see because we have a group, we could multiply from the left by g of lambda, and we get equivalently g dot of lambda equals minus g of lambda inverse acting on omega along delta of lambda to the tangent vector at each point here, and then again g of lambda. And that, of course, reassures us in this context that this really is a first order ODE for this curve in the group. Yeah?
G of lambda minus 1 shouldn't be there.
That is correct. Thank you. Thank you. Yeah, that's right. That's right. That's one. Okay? So, and in this form, it's obviously not too awe-inspiring. Now, however, this is still written in kind of this global way. In particular, we still have the globally defined connection 1 form here, which is very elegant, but for actual calculations, we need to look at a local trivialization in order to write down expressions we can further manipulate.
On the construction that you gave 1, 2, and you first choose an arbitrary curve delta.
That's right.
So it matches the projection, everything, and then you take this group G to make it into the curve you actually want to have.
That's right.
When we choose a curve arbitrarily, why don't we just choose the curve we want to have?
Well, because you don't know what the curve is. So that's right. So you choose one arbitrarily, and I say, well, take the one that looks precisely like this. I'm going to show you an example like this, and you write down explicitly, but you can choose an arbitrary curve totally ignoring what the connection 1 form is. And now what you want to obtain is a horizontal lift, which depends on the connection 1 form, but to guess that curve is very difficult. And to write down an arbitrary curve is very simple. And you may have reason to choose this arbitrary curve over that arbitrary curve because you can now quickly construct it or something like this. But then the question is, how do you get from there to the curve you want? It seems a little bit complicated to do it this way, but you see we reduce the problem of finding the horizontal lift of a curve. We reduced it to solving a first order ODE on the group manifold. Okay, so nothing to do with the principal bundle, and well, by appearance of this curve delta, the ODE has, but it's always the same setting. You go to this group manifold, you solve an ODE there, and you derive everything from it that you want. So so that's the way to proceed here. Okay, good. Okay, so in order to calculate, you know, whenever we calculate, we need to take numbers and to put down an object in terms of numbers, or to define in terms of numbers. And we do this by going to a local chart on the base manifold. So in order to further manipulate, to further, massage this ODE, we focus on a local chart. On a local chart U with coordinates x of the base manifold. So now, in addition to this local chart, choosing of this local chart, in addition, we choose a section sigma of the principal bundle. You recall that that means that pi after sigma is the identity on M. Now, such a section induces two things. So this induces two kinds of objects. So the first thing we get from this, we get a curve delta, and now here you get your arbitrary curve in this context. You get a curve delta as sigma after the curve gamma in the base manifold. So remember, we want to calculate the horizontal lift of gamma. So gamma is given in the base manifold. Now we have a section sigma. So maybe I draw a picture again. So we have our curve gamma in the base manifold from one point A to another point B. We clearly move along a number of fibers on the way. And now I chose a curve, a section sigma here, which to every point in the base manifold attaches a point in the fiber over that specific point in the base manifold. That's a section. And you see by defining delta as sigma after gamma, I get one such curve delta. Now I don't remember what the color for delta was before, but now the color for delta is green. Okay, so this is a green curve. This is a largely arbitrary curve. Well, I generated it from the base curve by the choice of an arbitrary section. Okay, so you say it gets worse and worse. First you tell me choose an arbitrary curve. Now you produce this one by choosing an arbitrary section. But well, you see the choice of an arbitrary curve here that projects down to gamma is equivalent to choosing a section, because with the section I can always go from gamma up there to the same fiber, which automatically ensures that projecting down the delta I get gamma again. And that was the only condition for our arbitrary curve here, that it projects down to gamma. So now we did it via a section. Okay. Now what we also learn from this is that if we now, for the such defined curve delta, if we look at its tangent vectors, what do we know? Well, this is a tangent vector. This is the sigma. And I know that if I take the tangent vector to the curve gamma down here, so let me take the tangent vector to the curve gamma in the base space at some point gamma of lambda, we know that if this curve delta has been produced as the image of gamma under sigma, that the tangent vector to delta can be obtained by the push forward of this tangent vector under sigma. So we can actually take the push forward of sigma of this tangent vector here, and what we will obtain is the tangent vector to the curve delta we produced thereby at the same point of the parameter space. Okay, so this is an immediate conclusion from here. So now, once we have that, we recall that in the ODE, we have the expression omega along the arbitrary curve delta applied to the tangent vector to the arbitrary curve. You remember that was one of the expressions appearing in the ODE, but which in the situation we produced now, we can write this x here as the push forward under sigma of the, so this is omega so the delta is sigma after gamma, right, of lambda. And we can write this here as the push forward under sigma of what? Of the tangent vector to the curve gamma at this point. This is what I just wrote down here. Agree? Aha. But what is the omega evaluate on this sigma star? this is exactly the definition of the pullback of the omega at the point gamma of lambda acting on this tangent vector gamma of lambda by definition of the pullback, right? But this gentleman here, and this is the whole point of having generated, or one of the points of having generated the curve delta here by virtue of a section, we know what the pullback of the connection 1 form via a section is. It's the, and I'm sorry, the section should have started only, should be a local section here. It's only a section on the local patch. This is nothing but the Young-Mills field gamma on U, which is defined by virtue of this section. So probably one should always write gamma of U, but it mainly depends on this sigma. So this is this one form, and this one form, of course, eats this tangent vector here. Okay? And the whole thing is Lie algebra valued. But if it's a one form, and this is acting on this tangent vector, and this is a tangent vector to the base manifold, I can, of course, use the coordinates I have just chosen. So I have here a mu, and here I have the gamma. Well, technically speaking, what I have is the let me write, yeah, it's the tangent vector to the curve gamma at the point gamma of lambda, but it's muth component. So this action I can, of course, write in this form, right? The action of this one form on this vector, because it's really a tangent vector to the manifold. And of course, I should say here, this is at the point gamma of lambda. Okay? Good. So I said this induces two objects. Well, this is the second object I meant. So one this, and okay, second, we already used it. It induces this gamma u sigma as the pullback of the one form. Okay, that's the Young-Mills field, which we already used in there. Okay, so that's the virtue, or this is the benefit of localizing the whole thing here. So going to some u in the base space, considering the situation there, being able to choose a local section of the principal bundle. You know, the global section would mean the principal bundle is trivial, which in general is not the case, but a local section we can choose, and thereby we relate this arbitrary curve via this section to this curve. At the same time, by the same section, we relate the one form to the corresponding Young-Mills field. Okay, so by going local, we can express this in terms of a Young-Mills field. Okay, so this is this part. And then, of course, in the special case, so again, in the special case, special but important case of a matrix group, the ODE becomes locally so what did we have? We had this G dot, right? So G dot of lambda equals minus, and now came this guy. So this is gamma. So I don't write u sigma. We know it depends on u sigma. Gamma mu at the point gamma of lambda times the tangent vector to this curve. Well, this is a very complicated way to write this, we could also, in local components of the curve under the coordinate map, could say this is the derivative with respect to lambda, right? This is certainly true in the chart. And then we had another g of lambda there, right? G of lambda. This is what this becomes. So you see this arbitrary curve business, where we may have been wondering why we take this arbitrary curve. This arbitrariness translates, or is here encoded in this section, and the section translates in a Young-Mills field, which is also only defined with respect to a section. Okay, so going to a Young-Mills field has to do with choosing this arbitrary curve. Another choice for this Young-Mills field, by virtue of another section, would lead to another arbitrary curve we start from. Okay, so at this level, apparently the arbitrariness has vanished, but of course it hasn't, because in the definition of the Young-Mills field, this arbitrariness is still encoded. Right. So anyway, so this is this thing, and we should never forget that this comes with the initial condition that g of 0 must be this particular g0 we determined or we constrained before. Okay? Any questions so far? So now, once we have an ODE with an initial condition, the question is of how to solve it. And this seems not too difficult because it's a first order ODE, but you see the coefficients depend also on the variable lambda, and that makes it, of course, difficult. Okay, so this cannot just be integrated. If these factors here, up to here, didn't depend on gamma, the solution would be just some exponential and that's it. Okay, but that's not the case. So the question is how to solve this. And well, a simple solution is we just integrate this up. But of course, that's not the final solution. So first step, we write down g of lambda, or let me now choose a different, let me choose t. G of t equals, well, g of 0 is supposed to be g0, so let's start with this. And then I write minus, and then the integral, so I integrate both sides, and this is just the integration constant, minus d lambda gamma mu of gamma of lambda, gamma dot mu of lambda. Well, and here is the g of lambda. So this doesn't seem to have brought us far because we integrated the whole thing over lambda, so that removed the dot here, integration constant here. We start here from 0 to t, so indeed if we plug in 0, we get the g0. So we integrate on both sides over from 0 to t d lambda. So no secret so far, but of course it doesn't solve the problem because the g we want to calculate appears here as a function again. So this is still recursive. Okay. Now, before we continue, just keep in mind, I mean, it's obvious, but the whole thing is Lie algebra valued, in particular because this guy here is Lie algebra valued. And because we're in a matrix group, the Lie algebra are matrices of the same size. One could say it's matrix valued. Okay. Now, of course, I emphasize this because if we should have fantasies of commuting several guys of this at several points, of course, not possible because we don't know whether it commutes or not, for different lambdas. Anyway, so this is the first step. And well, now how does this proceed? Well, of course, we can continue like this. We can start here. No, we can now do the following. We have an expression for g of t. The g of t appears here again, so we can just insert on the right-hand side this expression again, because the expression is valid. Okay? So, okay, maybe better this way around. Okay. So, so strategy. Insert this expression into itself. So there's nothing indecent about that. So we get g of t equals g0 minus integral from 0 to t d lambda, well, let's call, yeah, d lambda, gamma mu of lambda, gamma dot mu of lambda, and now I need to insert it into itself. So what I get a factor g0, that's this. Then I get a minus, but there's already a minus, so I becomes a plus, and I repeat this part of the expression, 0 dt d lambda, gamma mu of lambda is repeated, and now there comes another integral, which of course I can pull in front, integral d lambda, but I only plug in the g of lambda, so that only runs from 0 to lambda. Now I get here conflicts, so I call this lambda 1, I call this new one lambda 2. Then I keep the order, so I before had this gamma mu at the point lambda 1, and then I get a gamma dot mu at lambda 1, and then comes the gamma mu at gamma of lambda 2, gamma dot mu at lambda 2. Okay. G of lambda. G of lambda 2, right? Yes. G of lambda 2. Aha, okay, what have I achieved? Well, I made the whole thing more complicated without apparently achieving anything, because, well, this term can be calculated now. Could be all the time. This one can be calculated now. There is no more recursion in here, because this is just the fixed g0 from the beginning. Only in this third term do I still have this g of some lambda that's running, namely from 0 to lambda 1, that hasn't been determined. Now the strategy, of course, is to continue inserting. Well, for simplicity, we take this one, because they're both true. We insert this one again into here. And of course, what you get, so inserting again dollar into pound, so this is pound, and this is dollar. And so on, we get, what do we get? Well, let me try to, it's g0 minus, now we get here a simple integral, right, from 0 to lambda d, let me call it d lambda 1, or to 0 to t, d lambda 1, and well, let me call this entire thing here gamma of lambda. Okay, this is just a short form. This is gamma of lambda, well, it's gamma of lambda 1, okay? And the g0 I factor out in the end, so I take here the identity on the Lie algebra, okay? Or rather, g0, rather here, the identity here, minus this, then comes a plus. Now comes the integral from 0 to t d lambda 1, but here only from 0 to this lambda 1. d lambda 2, gamma of lambda 1, gamma of lambda 2, minus, now comes a triple integral, 0 to t d lambda 1, 0 to lambda 1 d lambda 2, 0 to lambda 2, this previous one, d lambda 3. Now come three gammas, gamma lambda 1, gamma lambda 2, gamma lambda 3, plus, and so on, more and more integrals, but at the end of every one is the G0. Okay? And it continues like this. This is what happens. Now, wouldn't it be fantastic if we got rid, or are there any questions so far? Yeah?
How do we get the 1?
Oh, that was this G0 here that I just reproduced by 1 acting on G0.
Okay.
So it's the identity acting on G0 gives you this G0. Now this integral is already Lie algebra valued and acts on G0. I just factored the G0 out.
Okay, yeah.
And that will appear repeatedly.
Yeah, I see. Yeah. So
Yes.
we just get the G0 at the beginning.
Exactly, exactly. And if you continue with this as a series, then we'll just have the G0 here. Now we would like to write this in, I mean, this is the solution, okay? So if you want to calculate this, you can calculate this to any arbitrary precision by continuing in this series. Now, it would be nice to massage this a little, and it's a little annoying that this integral here only runs up to lambda 1 instead running up to t as well. And here it gets worse. This runs to lambda 1 and this runs to lambda 0. The first thing we would like to do would like to convert this expression such that every integral runs from 0 to t. And that's a well-known trick. So you see what you have. You have here these lambda 1 and lambda 2. So lambda 1. So I do it for this integral. The rest will then be clear. Lambda 1 and lambda 2. And so the lambda 1 runs from 0 up to some t, which is given for all the integrals as a fixed number. So the lambda 1 runs over this range. And the lambda 2, however, only runs from 0 up to the current value of lambda 1. That means the lambda 0 runs like, yeah, so the combined integral runs over this domain. You agree? That's the domain of the double integral. And so the idea is that you can actually also let it run over the entire domain if you put a factor 1/2 in front. And you can let this guy, so you do the same thing in 3 dimensions, you can let it run over the entire the domain 0t, 0t, 0t if you put a 1/3 factorial in front. 1/4 factorial, 1/5 factorial. And so with that, okay, but what you need to keep, but now that's now the thing, if these were simply numbers, this were true, then we could simply write exp of minus, because we need to produce this minus, integral from 0 to t d lambda gamma of lambda. And this would act, so this entire square bracket would be this exp. So introducing an unnecessary bracket, but it clarifies which terms. It would simply be this expression here. You have then powers of this integral repeatedly. But the problem is, if you do this in these powers, how are the powers of this integral to be ordered? Because it's not the case that this is just this one integral times the other, because that upsets this path ordering. So it's not precisely an exponential. It is a path-ordered exponential. Okay? So the square bracket is the path-ordered exponential. Now, if you ask backwards, what's the path-ordered exponential? Well, you define it in terms of this. Okay, so the whole business with this domain change and in finding these factors of the exponential, this is very pretty to explain the notation, but it's also pretty useless because it's not the exponential, it's the path-ordered exponential, because that would be wrong, because these guys don't commute. So my argument here is actually slightly wrong. It would only apply if these guys commuted. Otherwise, you have to write down the path-ordered exponential, and that's actually defined like this. So therefore, the colon is here. Okay. So if you meet this path-ordered exponential, if you want to make sense out of it, you need to write down this. And then, of course, you would be crazy to integrate from 0 to t, and you do it from here to here, and then you save yourself from the 1 over n factorial factors of the exponential because they went away. Yeah?
How do you get the alternating sum?
Yeah, from here. No. I mean, that's the idea. Minus, plus, so here it is. Minus, plus, minus. So, of course, just if you put the... Okay. Okay? Yeah?
Does this converge in any way?
Sure. Yes. Yes, it should. Well, the point is you have this ODE, and the point of this ODE it certainly has a local solution. Okay? But because we're on a Lie group, this can actually be extended to a global solution. It's very similar to the issue with the left invariant vector fields, that they are complete. Okay? So in general, you wouldn't know, but on the Lie group, you do.
Okay.
That's it. Okay, but anyway, this is the explicit form here. The upshot of everything we said is that locally, the horizontal lift of a curve gamma and now I only consider its values in this local patch we had, and on which we have by our sigma a lift to the corresponding principal bundle, is given by the explicit expression, and that is what we were after. Gamma hat, not hat, gamma up arrow, horizontal lift of gamma is, so we wanted to generate this from an arbitrary curve in the principal bundle, but we did this by actually lifting the curve gamma to the principal bundle by some section sigma, which we chose. So that's our arbitrary curve delta. And on this one, we acted from the right by our g of lambda, by our curve in the group. However, this we recognized to be given by the path-ordered exponential of minus integral 0 to t d. Okay, now I wrote t. Now I need to write lambda here, because I wrote lambda here. Okay, so now I exchange the roles. That won't confuse you. dt, and here we had the connection 1 form, gamma, along the curve small gamma times the coordinate representation. So we have also from here, from this u, a coordinate representation into r dim m, and we take this coordinate representation and then of this curve, and then we can just take the derivative component-wise of this guy. but this whole path ordered exponential acts, well, after it was calculated, it acts on G0 and produces from one group element another one, and this entire right-hand side is the group element at the point, now I wrote lambda here again, this should be AT. This is the group element at parameter value lambda by which you have to move within the fiber of the principal bundle from this point in order to get this guy. Okay? So once again, the full picture is the manifold M. It's the curve gamma down there. It's the various fibers through which this curve runs. The other fibers are not of interest at the moment. We had this section sigma, so this is this gamma here that appears here in several places. Okay, we had this section sigma that takes us from the base manifold 2 points on the bundle there, and this sigma appears here, but you know it also appears here in, so I put the sigma up here, which means this Young-Mills field depends on this choice of sigma, and that is kind of reasonable, because if I have here, I want to find something that only depends on gamma, but I start from something that depends on sigma, well, that must be modified in a way that depends on sigma in order to get something that doesn't depend on sigma at the end. Okay, makes sense, must look like this. Then we get this arbitrary curve here. So maybe I show this one in blue. So this is the arbitrary curve sigma after gamma. Okay, and then I use this path ordered exponential here, always acting on the same G0 anyway, that depends on the point lambda, and that is what brings me by action of this entire, well, it's actually rather the, so I should rather make everything here green, okay? So by action of everything in the round green brackets, I am moved along the fiber to another point in the fiber at each point, okay? Why not going back here, also possible, okay? And the result, this white guy here, that is the curve that results from it. And that's the horizontal lift, okay? So this is how this works, and this is the guy you got to calculate. Okay. Okay. Questions so far? So then we have another definition of actually the central object we're going to use in parallel transport, in the definition of covariant derivatives and so on. Again, let gamma be a curve from 0, 1 into the manifold, and let gamma up arrow from 0, 1 into the principal bundle be the horizontal lift through, well, let's now indicate this by putting a down P here, the horizontal lift through a point P in the fiber over the point gamma of 0. Okay? This is gamma of 0, this is gamma of 1. This is the fiber at this point. Then the parallel transport map. T, which takes you from the fiber over the initial point of the base space curve to the fiber at the final point 1 of the base space curve. So this is the fiber here, right? Okay, so let me call this the initial fiber. Let me call this the final fiber. So this is really a map between some finitely separated fibers. Okay, it's not something differential. It goes from one fiber to a fiber that may lie far away, but which is connected by a given curve lambda. Then this parallel transport map, what does it do? Well, pardon me?
If you're using the endpoint, shouldn't it be the closed interval?
No. It's the lift through this point, and by the lift through the point, we always meant that you pick the point here, and then it's the unique horizontal lift that goes at the initial point through this P.
No, I meant for the curve gamma. Well, it's open or closed interval.
Oh, I'm sorry. This is I'm so used to writing the open intervals here, but here we really need the closed ones. Happy? Okay, good. Thank you. Sorry, I misunderstood the question. Okay, so now from this initial fiber, we may now take an arbitrary point. And what point do we associate to it? Well, we associate the point to it that corresponds to the horizontal lift of gamma, but there are several ones. Unless I specify what the initial point is, it goes through, it passes through. I do this here, but then I evaluate this at 1. So that means I arrive at this point over here. This point over here. This is the point gamma horizontal lift passing through at the initial point through the point P, but evaluated at 1. This is this guy here. So the idea is extremely simple. Pick two fibers and connect them by some given curve, and then there is a map that maps this point P to that point here in the other fiber. And to which point this P is mapped, I emphasize again, crucially depends on by which path you connect the two fibers. There are obviously many ways you can connect two fibers by a path. You can run around here as often as you wish, and then you go here, will yield you another map T. So the map T takes you from here to here. That's this map T. So it should be it should be labeled by everything. It depends on, it depends on the entire curve gamma. That's the point. It depends on the entire curve gamma. Where it starts, where it ends, what path it takes, and so on. This is the parallel transport map. Goes from the fiber over the initial point to the fiber at the final point. That's the parallel transport map. Now, the question is, and that's the key property of this guy, it induces a bijection between these two fibers. a set theoretic bijection. If everything is continuous, it will be a homeomorphism. If everything is smooth, it will be a diffeo, and so on. But speaking only set theoretically, because you can always choose what additional structure you want, it induces a bijection. How do we see this? Why is this true? Well, observation. T gamma is a bijection between the initial fiber and the final fiber, and this is essentially due to, if you think about it, the fact that the push forward of a horizontal space at some point actually is the horizontal space at the point P acted upon from the right by G. That means within the fiber, this guy moves you within the fiber here. And if you then look here at the expression of this parallel transport map, you learn that you're moved here in the same way, and really by moving from this point to any other point here, you can generate from here any other point there. And the T-map is, of course, equivariant with respect to that, and so you get a bijection from here to there. So that means, at the end of the day, where we come from a connection on the principal bundle, a connection on the principal bundle always affords you with a bijection between one fiber and any other fiber, depending on how you connect the two fibers. This is all in the principal bundle. Now, there was the question for closed curves, so let me say something about this. Considering the case of loops, that is a curve or curves gamma from 0 to 1 in the base manifold with gamma of 0 is gamma of 1. So you go to a certain point here, you have a fiber over here, and now you consider a loop down here, so you move away, but you decide to return. Okay? It's a loop in the base space, and it's a loop based at gamma of 0. Well, could call this little a in M. Okay, it's this point. And now, of course, you can again ask the question, if I start at a point P here, and I look at the horizontal lift of this curve gamma up here, where do I end up? And in general, one will end up at another point in the fiber. Obviously, one needs to return, but one ends up in another point. Okay? So start here and end there. And again, once you arrived here, you know that there is a unique little g in the group that acts on this P to produce this guy. Let's call it the G little gamma, because it depends on this curve gamma, and this point up here will be the starting point P, acted upon from the right by the little g depending on that gamma. Right? Okay, you get here by the parallel transport map, and there's such a g. And this g sub gamma is very interesting, and we have then a definition. Let A be a point in the base manifold, and gamma a loop with base point A That is, gamma of 0 is gamma of 1 equals A. Then the subgroup Hol at the point A and that depends solely on the connection one form on the principal bundle is the set of okay, so if I write it down locally, okay, I was tempted to write it down locally, but I think I will then run into trouble. What I need to do is I need to say this is the set of all the G gamma well, okay. Oh dear. So I need to express this guy over here. Okay, so before I finish this, I say I look at the parallel transport map for this guy, gamma, for this loop. And I know that that associates with a point, with any point P, the point horizontal lift through that point at 1. But I know because this is in the final fiber, and the final fiber coincides with the initial fiber, this is because we have a loop. Gamma is a loop. I know that this can be written as the original point I started from, and that there is a unique group element G sub gamma, I just call it like this, that produces this result from this P. This is the guy I wrote here. And I take all these G gammas which have this property. For all loops for some loop gamma yeah, for some loop gamma, full stop. Okay, so the idea is start where you wish and then take all possible loops and come back to there and see what results you get, but express the result by how far you had to move this point by a right action. And obviously this whole thing is a subgroup of the Lie group we're looking at, and that's called the holonomy group. Hol omega A is called the holonomy group of, well, of the connection, one form, or of the connection on that principal bundle. So this is because you asked about closed loops. So this is something you can do with closed loops, and that's indeed a special case. Okay. And the holonomy also gives you information about the topology of the manifold. So all of this, all we did happened on the principal bundle, okay? So don't be fooled by these simplistic pictures with these one-dimensional fiber. That was just a special case of a one-dimensional Lie group that I chose in order to be able to draw pictures at all. But in general, the fibers are the entire Lie group, and if it's higher dimensional, it's higher dimensional. But then, of course, the same ideas and general definitions apply. So thankfully, transferring the whole business to the associated bundle just rests on one single definition, and that is particularly simple, and then everything can be transferred. So we have the definition. Let P pi M be a principal G bundle and omega a connection 1 form on P, on this principal bundle. And now let further P sub F be an associated fiber bundle on whose typical fiber F the group G acts from the left by this object, by this action. So remember the total space of the principal of the associated bundle. So I should actually complete this. So there is a map pi F that goes to the same base space. And you remember how this total space was constructed. So recall that the total space of the associated bundle was constructed as the hang on a second. As the pairs of a P and an F in P Cartesian product F, where the hang on a second, how was this? No. It was these equivalence classes. Is that right? Okay, hang on a second. Confused here. Right. This consisted of these equivalence classes P comma F, okay, for P in P and F in F, where a pair PF was declared to be equivalent to a pair P prime F prime by definition if there existed a G in the group such that P prime was obtained from P by the right action of G, and F prime was obtained from the F by left action of the inverse of the G, right? So this was the construction for the associated bundle, okay? And now let alpha or let gamma be a curve with endpoint 0, 1 in the parameter space in the base manifold, and let gamma hat sub P be a curve in the principal bundle, which is the horizontal lift. The horizontal lift of gamma through, which becomes unique by specifying a point P in the principal bundle, through a particular point P, but that must be the initial point, so in the fiber over the initial point of the curve. Then, now the definition comes, so this was all preparation. Then the horizontal lift of gamma in the associated bundle, or to the associated bundle, that passes through, now we need to specify a point in the associated bundle that passes through the point PF in the associated bundle, is the curve, so we need a new name for it, gamma up PF, gamma up to PF instead of up to P, is a curve from 0, 1 to PF, and it's defined by gamma up PF of lambda is simply the element of the curve in the associated bundle constructed from gamma up of lambda, comma the initial f. That's it. So this is the horizontal lift of gamma to the associate bundle that passes through this point. That's the whole name of this object. And simply generated like this. Okay? It may appear odd at first that this point F it passes initially through remains there, right, throughout the curve. But remember, everything that happens in front of here by the equivalence relation can be understood as something that happens back there. Okay, so this is the definition. Okay, and so yeah, this defines this horizontal lift. And another definition, which I'm not going to spell out because it's totally obvious, is well, I can also spell it. Well, anyway, the parallel transport map T, which still depends on the curve gamma in the base manifold, but this is now the transport map on the associated bundle, and it starts in the fiber of the associated bundle. So it's this pi f pre-image, that's the bundle projection here, pi f pre-image of gamma of 0. It sends you to the pi f pre-image of gamma of 1. So it's the initial and the final fiber now in the associated bundle. And again, well, you take a point in there which needs to have this form PF, okay, and it's being mapped to the corresponding gamma up to PF through the point PF. So if we wanted to indicate the particular fact that this passes through this point, like we did before, we would indicate it here, and we take this guy and evaluate it at 1. There's, of course, again an element of the associated bundle, but now in the final fiber, then the parallel transport map is defined as. And again, also in the associated bundle, it will provide a bijection between the fibers, okay, which also in the associated bundle provides a bijection or homeomorphism or diffeomorphism between the fibers. Okay. So that means this is inherited very easily. Okay? And so the final remark to this section is the following. If F is a vector space, that means it's equipped with an addition and an S multiplication. Okay, let's call it an R. It is an R vector space. And the action, the left action of G on F is linear. Then this associated bundle PF is called a vector bundle. Well, it's just a very special case of an associated bundle. But what you can do now is, of course, fantastic, because now this is M. Now, this here are again fibers, but it's a different picture from the one I drew before, from the several ones I drew before, because now this fiber F is attached at every point. The fiber F, and the whole thing here is supposed to be a local picture of the associated bundle. And what you can now do, you can actually take a point here, and you can take a point over there. Like, for instance, you could consider a section of this vector bundle. A section of this vector bundle would be a field, an F-valued field on the base manifold. And now you can actually define a covariant derivative along a curve, and I only indicate it because it will be on the problem sheet. If you now want to know how this, say, blue section, so let phi be a section, if you want a local section, on this vector bundle, so that pi after phi is the identity on M, okay, and let this be a smooth map, a smooth section, then we can think of this phi, right, as a vector value, but not tangent vector value, but F vector, now vector in F, F-valued field. And now we can define a covariant derivative of this guy, because we can ask at this point, if I move in that direction here, so let's call this capital X, so X is an element of the tangent space of M at a point at the point A down here. So this is a point A in M, okay? And now what we can do, we can actually consider some curve gamma to which this is a tangent vector. And finally, this curve gamma, we can follow this curve gamma along its parameter value t, but we don't need to follow it very far. So you can now think of this fiber being very close, but we follow it for some t. And we can ask, how is this blue dot here transported to over here? Or you could also ask, how can you, if you walk this curve backwards, how can you transport here? But let's say, how is this guy transported over here, parallelly transported over there? And you know there will be a unique horizontal lift, gamma, up to PF. That's what we just defined. No? It's a lift of this curve into the associated bundle, and you'll arrive here. But now, because you have, and that's the point, because you have a vector bundle, you can now take the difference between these 2 points. You can then calculate the difference between the value of, the value of the phi at this point here, at gamma of t, and the value, the parallelly transported value here, and that gives you a number. And if you divide that number by the parameter value t down here, you have a differential quotient. This way you define a derivative. But you see, in the differential quotient, there is a minus sign. And the minus sign, that comes from here. That's just the additive inverse of the vector space structure on the fiber. I put this on the problem sheet. And this is the idea behind constructing a covariant derivative. So what do we learn? A covariant derivative can first of all only be defined on a vector bundle. How? Well, if we consider this vector bundle as the associated bundle of some principal bundle that carries some connection. Because if the principal bundle carries some connection, it has a parallel transport. That parallel transport is inherited, or it has a horizontal lift of the curves. This horizontal lift of curves is inherited to the associated vector bundle, and there gives you the means to compare this value with this value by comparing it in the same fiber, because you can only compare in one and the same vector space. And a special case of this special case is that this is a vector space of the dimension of the manifold, and you obtain by, in the way I showed it before, you obtain the tangent space this way. You understand the tangent space of the tangent bundle of the manifold as an associated vector bundle. And then, of course, the whole thing applies in the special case of this special case. And then you can inherit from the connection one form on your principal bundle a covariant derivative on the tangent bundle of the manifold, which very often is just called an affine covariant derivative. Right? This is the guy you use in, for instance, general relativity. But in quantum mechanics, for instance, you might take as this fiber, you might take the complex numbers. And then these complex numbers, they're a vector space, of course, trivially, a complex vector space in that case. And then a wave function can be taken to be a section of this C line bundle, which is just an associated vector bundle here. But if you know how to act on this guy, how this is associated to some appropriate, and we'll talk about this, principal bundle, you can have a covariant derivative here. And in fact, that is actually what you want in order to be independent of Cartesian coordinates. You need to understand the wave function as a section of the C line bundle over the base manifold that's associated to an appropriate principal bundle with a connection. Okay, so this is where all these guys, all this runs together, and of course, if you have non-abelian gauge theory, then you're still on the principal bundle, because then you have your gauge group, and then the Young-Mills field immediately is your non-abelian gauge field, right? The A mu. So our gamma sub mu is then the A mu of non-abelian gauge theory. Okay. So Young-Mills theory happens there on the principal bundle, but say what you need as covariant derivatives in general relativity or in quantum mechanics, this happens on associated bundles. Okay, so this is not exactly the same, but it belongs very close. It's very, very tightly connected. Okay, so this will also be on the problem sheet so that you get some practice in dealing with this. And next time I will finish the purely mathematical part. We'll talk about curvature. It's the curvature of a connection. And I'll also talk about torsion. But whereas curvature is defined for any connection on a principal bundle, torsion is only defined on associated bundles that have where there is an additional structure, a so-called soldering form. So a torsion is not as general a notion as curvature is. Nevertheless, we'll discuss this, and we'll come to the Cartan structural equation, and that then completes the mathematical part, and then we'll continue with some physics applications.